Hello. So now let's look at this rather simplified model of the laser. Even though it's a simple model, it captures the essence of what the laser action is. So I'll consider only two variables here and I'll represent them as so. N2 is the number of atoms in the excited state. In the state 2, right, which is our excited state. And Q is the number of lasing photons. So now let me quickly clarify what these and how these arise. So to begin with, for the atom, we have a two-level system, right? And what I have done for to focus on the lasing action, I have prepared my atom in such a way that most of the electrons are in the excited state, right? That is, I have somehow, I'm not worried about how at the moment, but somehow I have managed to put all the electrons in the excited state. So what I have generated is basically the population inversion. So in this limit where I have produced the population inversion, uh, my claim is that N2 is much, much larger than N1. And hence, I will, because of the situation, I'm going to ignore whatever is happening in the level N1. I basically do not care about the atoms in the ground state. The second parameter Q has got to do with the light field. So what we have done is we have chosen a cavity which is represented in terms of these two mirrors, and within this cavity there is our active atoms. Each of these is prepared in the excited state, right, through population inversion, and the light is bouncing back and forth within such a cavity. And part of this light that is bouncing back and forth is extracted as the lasing output. Now you see, when the atoms are in the excited state within such a cavity, they will be releasing light in sort of all directions because of spontaneous emission as well. We have not in any manner changed the spontaneous emission, the possibility for spontaneous emission. So you see, within this light, there might be modes which are not lasing modes. It is only these modes which are of interest to me are the ones which are the fraction of photons within the cavity that contribute to the lasing output. So you see, this Q is now the number of lasing photons, and I should qualify this within the optical cavity, within the resonator or the optical cavity. All right. So now that we have got these two parameters, let us just see what is the evolution of these. So what I'm going to write down is basically rate equations. Rate equations are first order differential equations that basically allow you to intuitively capture the loss and gain, uh, or the creation and annihilation of uh, these entities. So for example, if I'm looking at the photons in the cavity, so if I'm looking at number of photons dq by dt, the change in the number of photons I'm saying is arising out of two things. That is, the number of photons is increasing by, let's say, some constant a, and it depends on the number of atoms in the excited state as well as the number of photons within the cavity. You would be able to identify this process as that of stimulated emission. Remember, stimulated emission not only depends on the availability of the atoms in the excited state, that is what is uh, captured by its dependence on N2, plus it depends on the incoming number of photons themselves. So if the incoming number of photons were missing, you would not be having the stimulated emission. So stimulated emission requires that we have both the number of atoms as well as the number of photons uh, governing the process. So this is how remember that the sign in front of this term is positive, and you have the second term, which is the loss term, which I'm saying is some coefficient b times q. So this is the loss of lasing photons which has been extracted from the cavity, right, as lasing output. So if I'm looking at, so in other words, if I'm looking at the number of photons and its change, the number of photons increase within the cavity due to stimulated emission, right, arising from this term, and the number of photons decrease because the photons are coupled to the outside world. Let us look at the second parameter, which is the number of atoms in the excited state. Right. So I'm again writing down a first order differential equation dN2 over dt, which tells me how the number of atoms in the excited state are changing in time. And I'm saying that obviously if the atoms, because of stimulated emission, contribute to the generation of cavity photons, at the same time, because of the generation of the cavity photons, that is this term, what happens is that the number of atoms in the excited state decreases because of stimulated emission. So what you have is exactly the opposite term, which is the same coefficient A times N2 times Q. This is the loss of atoms in the excited state due to stimulated emission. And of course, we have not shut down spontaneous emission. Remember that the other competing process when the atom is in the excited state is that it comes down to the ground state spontaneously, and that simply depends on the number of atoms in the excited state. So that is minus F times N2, plus remember that to create inversion, I will have to employ some mechanisms of pumping. It is not going to come freely, so I add a term which is plus P. And so if you look at this equation carefully, what you would see that the first term is arising due to loss of atoms in the excited state due to stimulated emission. The second term is arising due to loss of atoms in the excited state due to spontaneous emission. And the third term is basically the pumping term that puts the atoms in the excited state. Carefully look at the signs that govern the increase or decrease of these various terms. So Similarly, I will also write down in my previous equation, I will write down, so this term is arising out of the lasing, the loss due to the lasing output. The photons are after all extracted out as the lasing output, and this increase in the number of photons is of course again through stimulated emission. So what I have done in this process is basically I have ignored everything else that is happening around. This is a very idealized and rather artificial situation to look at something as limited as this. To create this scenario, one will have to worry about pumping, one will have to worry about how the photons are coupled outside the cavity, one will have to worry about stimulated emission, the competing process of spontaneous emission. There might be other non-radiative decay mechanisms or excitations which I have ignored. The fact that some of the atoms might be in the ground state where absorption will dominate, that is the light, the lasing photons which are generated is being absorbed back by the atoms which are in the ground state and so on. So there are all these other complications which I have at the moment ignored, and that I have to be very well aware of. Another note of caution, that all these constants which I have introduced here, that is the constant A, which kind of governs the gain of the number of photons, the constant B that governs the output through the cavity, the constant F which governs the spontaneous emission rate, and the pumping. All of these are constants which I need to justify and need to calculate them carefully. The rest of the course is going to allow us to calculate uh, these quantities in earnest. So these are constants which I have just assumed and I have not justified them in any manner. The second important note which I want to also emphasize is that uh, the equations that I have written down are indeed first order differential equations, and they are coupled because you see clearly that uh, the dependent variables q and n2 are there in both the equations. These are uh, these are differential equations that govern the time evolution of these quantities. The other important thing is that these are nonlinear equations. That is because we have got here sitting with us this product, right? This is the product of n2 times q, which is there in both these equations, and this is the nonlinear coupling between the two. And we cannot disregard this nonlinear coupling, and that is why the atoms in the field are very strongly linked within a laser. So I will write that down here as the nonlinear the nonlinear we identify the nonlinear term, which is basically n2 times q. So this identification is crucial. Right, so now let us analyze these two equations in the steady state. So I'm looking at steady state. That would mean that I have created now my lasing system, and I want to operate this lasing in a manner that doesn't change in time. That is, in the steady state, I would have no change in the number of excited atoms. I would have no change in the number of lasing photons, and hence that is the situation of a constant output from such a laser is what I am now going to focus on. So the condition I write down mathematically is that dq over dt is equal to 0 and dn2 over dt is also equal to 0. So this is a steady state condition that I am going to invoke. So let's take the first equation, right? And set dq by dt to 0, and you will see that quickly I can come to this relationship that my N2 should be equal to B by A, and this quantity is what I call as N2 threshold, right? So it appears as though in steady state, the number of atoms in the excited state have to take this value for me to arrive at a steady state in the photon number. Now clearly, if I look at this equation again, if the value of my N2 is less than B by A, that is, if N2 is less than B by A, clearly I will see that dq by dt will become less than 0, which implies laser would shut down, right? Because now the number of lasing photons would decrease and the laser would shut down, right? So it is important. That is why I am calling this value of B by A as the threshold. This is what happens when we put the steady state condition in the first equation. Now let's put the steady state condition in the second equation, right? In that case, what I will do is also remember that we are taking the steady state for both of these quantities. So I will also put in N2 value as the N2 threshold value and rearrange my second equation. You can do this, and with little algebra you will see that Q happens to be equals to P by B minus F by A. So in order that I get steady state output, I have got now a constraint on something called the steady number of photons that are coming out, or lasing photons that are generated, which is my Q. And similarly, I have got a steady number of atoms which I need to maintain in the excited state for me to get a steady state output. So what do we learn out of this? So let us imagine that what is the minimum number of photons that one can have, right? So the minimum number of photons that is possible is Q equal to 0. Now if I set Q equal to 0, what it means is that I get essentially a constraint. I set this Q equal to 0 and I'll see that P happens to be of the form F times B by A, which by the way, we know that F times N threshold, right? N2 threshold. So what it is telling you is that the minimum the minimum amount of, let's say, threshold pumping which I require to generate at least one photon is that my pumping rate should be larger than the loss per atom, which is the loss through spontaneous emission. So I'm looking at the minimum number of the minimum pumping rate to be F times, which is the rate at which spontaneous emission is happening, times the number of atoms at threshold. So I need to at least offset that much to produce just zero number of cavity photons. So if I do something more than this, if my P threshold is larger than this, I will be able to generate non-zero number of lasing photons, right? So that is a very important lesson that we have, and we quickly, it allows you to understand that spontaneous emission is actually playing the spoil sport. It is indeed is associated with the loss in lasers. Now, let me also uh, give you a slightly different perspective, which is that imagine you had a laser in which there was no spontaneous emission. In such a situation, the lasing would never start. That is, you require one spontaneous emission photon to be captured by the cavity and becomes the mode of the cavity, and hence it bounces back and forth within the cavity, collecting more of its own kind, and hence the existence of spontaneous emission is fundamental to the beginning or the seeding of the laser. And without spontaneous emission, the seed for the laser will not be present. So spontaneous emission in that sense is something that we need just a little bit, but not too much so as to overwhelm the system. That is why you would have heard this word that we look at states within atoms which are known as metastable states. That is, states which are long-lived, and hence the rate of spontaneous emission is significantly less from such metastable states. The other important comment which I want to make is that for these above equations, there happens to be no general solution for these coupled nonlinear equation. And if you do find one, please let everybody know, and you will be doing an immense favor to the scientific community. So there are no general solutions because of this inbuilt nonlinearity in these equations. It allows you to basically understand how this lasing works. To justify all this, we will actually have to go through the whole course, and we will talk about a variety of aspects in the course, such as gain, loss, threshold, steady state, the line width, the notion of saturation, the output power. Then we will talk about mode locking, tunability, stability, and all these other aspects that need to be put together for us to realize and understand the basics of a laser.